All right, guys, today we're going to look at combination circuits. So we've already worked on straight series circuits where it never branches off. And then we worked on just parallel where it all branched off. Now we're going to do what's called a combination circuit where you have some things that are wired in series and some things that are wired in parallel. And so first you have to figure out, well, what's in series and what's in parallel. Remember, series is where it has not branched off. So if I start on my long battery terminal, which is my positive terminal, I'm going to follow the circuit and I get to this point here. And there's obviously more than one path it can take. It can go this way through the 12 ohm resistor, and some of the current can go through the 18 ohm resistor. Okay? So because I have a choice, I have two branches or two paths for the current, that tells me that that part of the circuit is a parallel. All right? So let's say the current has gone through these two branches. More will go into the 12 ohm than into the 18 ohm because it takes the path of least resistance. So now I'm here. It's come back together again. So the current is all together again, and now it's coming through a 10 ohm resistor and continuing on and going through the 14 ohm resistor before it comes around and gets back to the negative terminal of the battery. So what that tells me is the 12 and the 18, yes, the current split here. But now the current comes back together and it never splits again. So the 14 ohm and the 10 ohm resistors are in series to each other. So this part here is series, and this part here is a parallel. Okay? So now that I know that, now that I've established that, my first step is to figure out what is the resistance for the parallel. I have to break the parallels down first. So I'm going to use the 1 over R equals 1 over 12 plus 1 over 18 to figure out my parallel. Okay? This gives me that 1 over R equals, when I add 1 divided by 12 plus 1 divided by 18, I get 0.138888888 repeating. So I'm just going to say 0.139. Okay? But remember, the resistance is in the denominator here, and we can't keep it that way. We've got to flip that. So I hit the X to the -1 button to flip it, and I get that the resistance is 7.2 ohms for the parallel. Okay? It's 7.2 ohms. So if I know that this whole thing is equal to 7.2 ohms, now I can treat that as if it were in series with these two. So now I can say, okay, well, that's my parallel. So I have a new circuit that looks kind of like this, where I have 14 ohms, 10 ohms, and 7.2 ohms. I treat it that way. I treat that parallel as a one resistor that has 7.2 ohms. So now I can say they're in series with each other. And so to find the total resistance for the entire circuit, I add 7.2 for the parallel plus 10 ohms for the second resistor plus 14 ohms for the third resistor. And I get 10 plus 14, 24, plus 7.2 is 31.2 ohms. So that's my total resistance for the circuit. And remember, I try and do it in a step-by-step logical manner, because then whatever I get here, in other words, the 31.2, I'm going to use in my next step. So now I want to find the total current in the circuit. How much current is going around this whole circuit, even if it splits at this point. Just in general, how much current I have. So I use Ohm's law, and I take my voltage from my battery and divide by the resistance that I just found in the previous step, my total resistance. So I'm going to take 35 volts and divide by 31.2 ohms. 35 divided by 31.2 gives me 1.12 amps. 1.12 amps. Okay? Now, I know that I have 1.12 here. I have 1.12 in these series resistors. I don't have 1.12 in each branch of the circuit, of the parallel part. It has split at that point. So now I'm going to want to find out how much went into those branches. Okay? So my next step, now that I know the total current, my next step is to find how much resistance does each part of that circuit has. So I'm going to find my resistor for my voltage for the parallel is equal to the current in the circuit times the resistance for the parallel. So my current in the circuit we said was 1.12 amps. And we had said before in step 1 that the resistance for the parallel was 7.2 ohms. So 1.12 times 7.2 gives me 8.06 volts on the parallel. And I always like to make a note that that's on the parallel because I'm going to need that in the next step. So if I denote it up here, then it's very easy to find when I'm going to do my next step. I still have to find how much voltage each resistor got. So for the 10 ohm resistor, I'm going to take the current times the 10 ohm resistor. So 1.12 times 10 gives me 11.2 ohms. I'm sorry, volts. 11.2 volts there. And for the 14 ohm resistor, I'm going to take 1.12, times 14 ohms. So 1.12 times 14 gives me 15.68 volts. If I add all these three together, I should get 35 or very close to it because of conservation. So if I add 11.2 to 15.68 and then add an 8.06, I should get very close to 35, and I do. I get 34.94. So approximately 35. And that meets Kirchhoff's rules. My last step is to find the current in each branch. In other words, how much current is in the parallel? Okay? So how do I do that? For the branch that has 12 ohms in it, I'm going to take the voltage on the parallel and divide it by the resistance in the branch that I'm looking at. Okay? So my voltage on the parallel, that's why I made that distinction up here, saying that the 8.06 volts was the parallel, because it's very easy for me to come back up here and go, okay, it's the 8.06 that I need. Otherwise, you'd be like, well, do I use the 11.2 or do I use the 15.68? What number do I use? But by knowing that that's the parallel, that's the one I want. So 8.06 divided by 12, because that's the resistance in the branch, I get 0.06 divided by 12, 0.67 amps. For the 18 ohm resistor, I'm going to do the same thing. I expect it to be smaller because it's got more resistance. So I'm going to have 8.06 divided by 18 ohms instead of 12. So 8.06 divided by 18 gives me 0.45 amps. Now if I add these two together, 0.67 plus 0.45, I get 1.12 amps, which is what I had to begin with. So it didn't split evenly because the resistors are not the same. If the resistors were the same, it would split evenly. But it split more going into the 12 ohm resistor than into the 18 ohm resistor because it has less resistance. So it's going to allow the flow of electrons easier. But it still has to total what you had to begin with because we can't destroy charge and we can't create it due to conservation. All right, and so that's the solution for that problem. Now, if I asked you how much power was used by this resistor or that resistor, it's very easy to figure out using any of the power equations because now you know the current and the resistance for each one. Some people like to make a little table. I've seen this done where they'll take every resistor, like they'll do the 12 ohm, 18 ohm, 10 ohm, 14 ohm, and then do V, I, R. So they fill in for each thing. So for the 12 ohm resistor, we know that the current's 0.67 amps. The voltage was 8.06 volts on that branch. The resistance is 12 ohms. That one's given. Okay. For the 18 ohm, we know that resistance is 18 ohms. You kind of don't need the resistance column because I'm giving you that over here. Your current is 0.45 amps. Your voltage also 8.06 volts. For the 10 ohm resistor, again, the resistance was really here. I already had it, so I didn't have to rewrite over there. That was just mine off the top of my head messed up. The voltage on this one was 11.2. The voltage on this one was 15.68. I'm getting that from the step 4 up here. And then the current on these, because it's a series part of the circuit, they were getting the full 1.12. So basically the results we found through the problem you can put into a little table. Some people like to do that to make it easier to read. It's up to you. Okay? All right, second example. And the reason I'm doing a second example of the same type is because I don't want you to think that every single series parallel combination is going to look the same. Okay? And this one here, we have the voltage on the battery is 6 volts. That's given up here. My first resistor is 2 ohms. My second resistor is 8 ohms. My third resistor is 10 ohms. And my fourth resistor is 14 ohms. Okay? Now, if you look at this one, some of you might go, well, what are these doing here? It's kind of weird looking. Well, follow the positive terminal. Always start at the positive terminal. Go around. When it gets here, it is splitting into 3 branches. This one, and this third one here. Okay? So on this branch, we have 2 ohms. On this branch, we have 8 ohms. On this branch, we have a 10 ohm and a 14 ohm on the same piece of wire. So in other words, these two are wired in series with each other, but they're part of a parallel because this whole branch is in parallel to this and to that. Okay? So my first thing that I'm going to do, because those two are in series with each other, I have to add the 2 resistors that are in series. So I'm going to find my resistance to be for the series 10 plus 14. Because remember, when they're in series, you just add them. And so this third branch here is equivalent to 24 ohms. And now I can do the next step, which is to solve the parallel. So even though I give it to you in steps, realize that the steps can vary a little bit depending on what your circuit looks like. So I have 1 over R total is 1 over 2 plus 1 over 8 plus 1 over 24. Notice that I don't do 1 over 10 and 1 over 14 because I would assume that the 10 and the 14 were on separate branches. And they're not. They're on the same branch, so they have to be added together. Okay? When I work this out, 1/2 plus 1/8 plus 1/24 I get 0.666666 repeating, but I have to invert that. So it comes out to be 1.5 ohms. And that's my total resistance for the circuit. Now it says, using Ohm's law, find the total current. Well, the total current is going to be the voltage from the battery divided by the total resistance in the circuit. The voltage from the battery is 6 for this problem. The total resistance I just found to be 1.5. So 6 divided by 1.5 is 4. I have 4 amps of current flowing in the circuit. Okay? Now I'm going to want to find the voltage for each branch and the current flowing through each branch. Okay, so the voltage for each branch is going to be 6. I know that because it's all part of a parallel. So in other words, for R1, voltage is I times R1. The current going in there, I don't know it because it has to split. That 4 amps is going to split. But I do know that that is part of a parallel and that each branch of that parallel is getting the same voltage from the battery. So it's going to be 6 volts. I know that 6 volts is going on that branch. For R2, the same thing. I know that it's going to be I times R2. Again, I don't know how much current went in that branch yet, but I know that it's getting the full 6 volts from the battery. The third one, the third branch, R3 plus R4, both of them together, is getting a total of the 6 volts from the battery. In order to figure out how much R3 gets by itself and how much R4 gets by itself, I need to find the current first. Okay, so I've got to move on to step 5. So step 5, this one's a little bit trickier. That's why I want to do this as an example. Step 5 is to take each voltage for the branch and divide by the resistance in the branch. So for the first one, I'm going to take 6 and divide it by 2. This is for our I1. 6 divided by 2, I'm getting 3 amps in that circuit, in that branch. For the second branch, for I2, I'm getting 6 divided by 8, which gives me, that's 3/4, so it's 0.75 amps. Now the fourth one, you could do one of 2 ways. 3.75 and your total is 4. That means 0.25 must be in the third branch. Or I can just go on with this step and do the same thing I've been doing. 6 volts divided by 24 ohms, because the whole branch has 24 ohms, gives me 1/4, which is 0.25 amps. Because remember, this has to total 4 amps. Okay, now I can come back down here now. I can do this. Come here to find the voltage on each resistor. R3 and R4. Because now I know the current. I'm going to take the current times the resistance, R3, to find that one. So the current is 0.25 and R3 was 10. So 0.25 times 10, 2.5 volts is going on that resistor. And then R4, I'm going to say the same 0.25, because remember these are in series with each other, so they have the same current, times 14 goes on that resistor. And that gives me 3.5. Because remember, this has to add up to what was on the branch, the 6 volts on the branch. And so you found the resistance on each, the voltage on each resistance. A little bit trickier. This is a little bit trickier than the other one. But I just wanted to show you that they can vary. They can get a lot more complex. This is the level we have to do for honors. If you take AP, they can get even more complex. If you become an electrical engineer, they get a lot more complex. But just giving you an idea of the basis of where these values are coming from. Okay, so that kind of gives you an idea of how to approach these vectors, and you're going to have some problems to practice on, and we're going to be practicing for a few days so that you become very comfortable with these before you take your test, which is going to be on May 8th. Okay? May 7th, Thursday. All right, thanks. Have a good day.